Right, I think we'll get underway. Good evening, everyone, and thanks for joining us this evening. Just to introduce myself, my name is Philip West. I'm the current chair of CIBSE North East. Just a couple of items before we let Brian get away. Just if anyone's got any questions as we go through the presentation, please use the conversation box to put your questions in, and what we'll do is at the end of the presentation Brian will work his way through the questions and answer them as best as he can, and then you can ask any additional questions as see fit from any of the responses that he gives. So yes, I'll pass you over to Brian to get away with the presentation, and yeah, we'll have a Q&A at the end. Thank you.
Good evening, everyone. I thought I'd leave my camera on so you can actually see us before I start this, because it's unfortunate that I can't do this in person, but that's the way of the world at the minute. So I'll just share my screen. Right, hopefully everyone can see that now. So tonight's talk is on drilling for mine water heat. From a drilling contractor's point of view, it's pretty new, not new technology, but a new idea, or an idea that's being pushed more recently. So I thought that I'd talk about how we do it and some of the challenges that are involved, and some of the things that are coming up now that these projects are taking off. Things that are coming out of the woodwork and need to be resolved or planned for. A little bit about me. I'm Brian Laycock. I'm Associate Director at Dunelm Geotechnical. I'm a drilling project manager for Hebburn Mine Water Heat Scheme. I also do. I'm also a project manager for general site investigation works on small to large scale site investigations. And I look after operations out of the Durham office at Dunelm. My role, this is my role in these sort of works rather than my general role, is to work with the drilling contractor to formulate a design safe methodology for constructing the boreholes, to create the documentation required to meet industry regulations, and a method of validation for the construction process of the boreholes. Project management during the construction phase, including all the health and safety, transfer of data to the client's technical team and the client, changes to the well design, and commercial elements, both client facing and my supplier facing. So a bit of everything. Everything goes through me essentially.
Sorry, Brian, just a quick one. We can see your sort of presentation screen rather
than sorry.
Your screen, yeah.
One second, I shall switch my screen. It's an amateur mistake. Amateur mistakes. That better?
Yes, yeah, that's perfect.
Perfect. Sorry, amateur mistake. Mine water heat schemes that I've been involved with. Pardon the spell mistake. Louisa Centre at Stanley, which was a pilot hole, and currently the Hebburn Mine Water scheme, which I've mentioned. I didn't really know what everybody's knowledge of mine water heat schemes would be, or how they're done, how they're drilled for. So I thought I'd give a basic overview and then focus in on the drilling elements. So what is a mine water heat scheme? It's an abstraction well, a reinjection well, an energy centre, a heat exchanger, and then the energy spread out through a heat network. Generally, the abstraction wells drilled to a deeper coal mine, taken up to the surface, put through a heat exchanger, and then it's put back down through the reinjection well into a higher seam, taking the energy out of it. My expertise is in drilling the wells themselves. I don't do anything to do with the heat exchangers or the networks themselves. My expertise is just drilling the boreholes and planning the boreholes, which are then used further down the line. Where can it be utilised? Obviously, in quite a lot of the UK, there's a lot of former coal fields, a lot of which I do investigate in my other role in site investigation, looking at potential collapsed workings and for future developments. spread across the UK and near a lot of urban environments in the north, which is useful, as the energy is obviously only useful next to urban environments where it can be used. But this does actually give us some challenges, which I'll discuss further down the line. My presentation, what I thought is I'd have a look at what desk study work is prior to the job even getting to my desk, or us tendering for the work. I'll just give a brief overview of that, because that's not really my expertise, but I know a bit about it. What considerations I look at when we're designing the borehole at tender stage, the documentation required prior to starting the works, safety systems, how do we construct the borehole, and then challenges of drilling for mine workings. They have their own particular challenges, which I'll discuss. It's not just like drilling a borehole into an area of rock, which could be miles. You're aiming for discrete targets, so that they do have their own challenges. Right, before the job ends up on my desk and we've hopefully tendered and won a contract with a client, the client's technical team, who they'll have employed, will have done a lot of desk study work. Looked at abandonment plans, looked at where the old mine workings are. This is obviously really important. We need to be directly over them. There is a discrete target, so we need to make sure we're over those. So when the mines were in operation, they've surveyed them, and these plans are still available. Obviously, a lot of the time they're beautifully drawn, hand drafted plans like this. So these need to be looked at before the start. Historic borehole records in the area. There's plenty of them on the BGS website. Some are publicly available, some aren't. They go back quite a long time in history, and the further back, the harder they get to interpret, unfortunately. The level of actual detail on them varies as well. There's not, this one, for instance, has just got the strata, which is useful, but there's nothing about water, so which is obviously important. It might tell you if it's intact in that area or not, and what's being mined, but it also gives you its depths, which is useful, but there's nothing on water, which it would be quite useful. This data is then overlaying over a modern topography. So they're taking the abandonment plans we've got with site, which would have to be fluid. You have to choose that based on your abandonment plans, really, but there might not be areas available. And they basically choose the targets based on that. So you're going to need a deeper workings and a higher up workings to re-inject. So your abstraction being the lower. From this, you can choose your potential well paths. That's important because the aiming for the deeper mine workings, you don't want to come across shallower workings, if possible. This creates a lot of difficulties when drilling. It leads to extra conductor casings being used, or potential cement jobs, which can be tricky and not guaranteed to work. So your well path design is quite critical. And to aim, as you can see, the red line aims to avoid the high main in this instance on this job, and contact with the Bentham seam below. But on the green well path, which will be the re-injection well, it aims for the high main. This is very critical, and obviously it's location dependent. So the desk study work is vital in choosing the best location for when it comes to doing these works. Other data sources, geology plans, obviously, shaft data, coal authority monitoring wells and pumping data. This can give you water chemistry and temperature locally. Local mine water heat schemes, that might be a thing in the future. Once there's more of these things, will there be knowledge sharing? The temperature and water chemistry is obviously very important, though, to check whether it's viable. And the data is dependent on location. You might be lucky and be close to a really good data set, you might be unlucky and not have much data in the area and rely on data from quite a distance from your site. This makes planning the job a lot more difficult because a lot of your details of your design aren't set in stone because you don't have very fine detail to start with. And essentially, once you start the job, you've got to be flexible in your approach to changing the design slightly, depths, etc. as you go. Documentation required prior to starting the job. This is very very up in the air at the moment. Different jobs on a personal level, and from what I gather from what I listen to from other people in the industry, is that there's a lot of variation currently in what documentation is required before starting one of these jobs from the drilling contractor point of view at that point of the job. Some clients, there's no current set in stone guidance about what you have to provide. So some clients are very risk averse and are asking for everything. Other clients understand the risks and are halfway, and it's very fluid at the moment. And I'll talk about this later once I get to the drilling challenges section. So a list of documents that require completing on a job that I've done. A mine gas management plan. This is vital, and I would never expect a job to go ahead without a mine gas management plan. It's the biggest safety concern on site, is we're aiming for mine workings that hopefully, if we interact with them, know have been worked, so there is a potential for mine gas. So that's important. Casing design, basis of design in the detailed drilling program are more oil and gas well orientated documentation, which have creeped into this sort of work, in the sense that you're drilling into a source that may contain gas, a hydrocarbon, and so a bit of oil and gas well guidance has creeped in. A design verification plan, it's a construction project, so how are we going to verify everything we install? A construction phase plan, obviously. Process documents, which are essentially an oil and gas well risk assessment method statement, site waste management plan, and noise, dust and vibration monitoring plan. Mine gas management plan. So how do we protect operatives and local residents from mine gas releases or potential mine gas releases? The jobs I've done, one has produced a little bit of mine gas, another one we've had nothing. It's just a potential, but we'll have to plan on the worst case scenario. What are the potential flows and concentrations of gas? So as you can see, there's a kind of an overview of some mine gas that the worst case mine gas we could have had on a site, and the trigger levels and action levels that are next to them there in that table. And as you can see, they're well over the action and trigger levels. So you do need to put in mitigations and processes in place before you can just drill into these mine workings. How the level of mitigations is another thing, but you definitely need to take it into consideration. There's no avoiding that fact. Obviously, the gas levels do pose a risk of explosion, fire and asphyxiation, not just to site staff. What are the pathways? So this is an overview of a drilling site, the operations that we're doing, the pathways and the locations of where the gas would appear. The job isn't just drilling. There's all sorts of different activities we have to do during the job, including things that have the potential to cause a fire explosion, such as welding the casing together. The pathways, release up the borehole column itself, a release of gas through fractures through the rock, through the natural strata, and then into adjacent buildings, and releases from gas from solution, which would happen at the mud tanks when we're drilling. The receptors, as I said earlier, the aim of this is to provide energy to urban environments. Therefore, a lot of these sites are going to be in and around other buildings which contain people. If these buildings have basements, they're more susceptible to the mine gas migrating into them through the strata. So you do have to think about how we protect not only the site operatives, but members of the public as well. So how do we do this? How do we protect the operatives and local residents? How do we monitor the gas? How do we intend to control any gas release? What pressures of gas can the well produce? And is there a safe location to vent the gas on site? So the first thing that I did when we set off to do this was get a dispersion model for the site produced. I provided them with the concentrations and the flow rates that I just shown you. And I gave it to some people who ran a computer model for me with 5 years of weather data. And they produced a diagram like this for all the gases. I've just got the one here for CO, but they produced one for all the gases. And we chose a location on site. We checked that it wouldn't leave the site boundary, and then chose a location on site where to put my vent, which wouldn't leave the site boundary and was away from the nearest receptor. So the block in the blue block in the bottom left hand corner is actually a tower block. So we try to avoid having it there. And it's also got to be away from equipment which could cause a fire as well. Well control. How am I going to control my gases? The primary well control on the jobs I've done is actually the water in the borehole itself. I've always got to maintain a positive head of water in the borehole to suppress the gas. This requires having one well volume of water on site at all times to top up the borehole. Process and procedures to confirm the well status before the end of shift. So when we switch off the drilling rig on a night time, we don't just switch off the rig and walk away. We've got to monitor the borehole to make sure the water level returns to its natural groundwater level. The problem with this is that if we're using thick drilling muds, it can take quite a long time. So there's like a management process with different scenarios. Before we leave site, we'll have to stick to one of those scenarios and inform the night watch staff what scenario we're under, so they can monitor the borehole in the night time, and if required, continuously trickle feed water into the borehole to create a positive head. It may be required overnight. To protect the operatives, we are using a wellhead diverter in venting. That's a diverter there in the blue. That bolts to the top of the conductor casing. The black rubber seal, column it is rubber, creates a seal around the drilling rods. It's not completely gas tight. It's not meant to be a closed in system. It does get pressure tested, but it's not designed to completely shut in the well. That's not really a recommended thing to do. If you start closing in your boreholes, then everything that you then put on the borehole has to be pressure tested to the maximum pressure within the borehole. All we want to do is to be able to control where the mine gas goes. So if the mine gas came up at the location of the drilling rig, I want to divert it away as quickly as possible from the drillers and send it somewhere safe. So the mine gas would come up. It would be stopped by the black rubber seal, which sits in the top of that diverter, and it would come out the pipe you can see on the left hand side. That pipe goes to the drilling tanks. The drilling tanks, there's less operatives there. There's less equipment which can create a fire as well. It gives the driller a time, if an alarm is sounded at the drilling tanks, gives them time to switch off and isolate all the equipment on the drill floor before it would make its way to where there's combustion engines and things like that around the rig and electrical equipment. With regards to protecting the public, the way we do that, so we prevent gas migrating to adjacent properties, is what we do in site investigation as well. We simply install conductor casing into the rock, but in this sense, because we're going to drill a permanent borehole, we cement it into the ground. This creates a seal. Any gas, once we've drilled into the rock, cemented it in, we are just drilling through that. Any gas release when we hit a mine will then just come up that column. It can't escape into the other strata and end up in the basement. Before we put in that conductor casing, we actually put gas monitors in the local buildings in the basement. And in a case of jobs I've done recently, we've actually locked basements and actually prevented access while we've been drilling. And to get access, they've had to come and get our site manager, who then checks the basement with a gas monitor before they go in there. Obviously, we've got a mine gas management plan. There's a management structure in place, emergency response plans, a form of the local emergency services of the emergency response plans, communication with the public. So on the Hebburn job, we actually do have an audible alarm, which the residents can hear. It's about 150 decibels, so they can close their windows. So communication's important. We don't want them panicking, and want them to know in advance of what the procedures are. Out of hours well control, which I discussed. And then independent, IWE is an independent well examiner review, which is daily, and verification, which I'll discuss what their role is. And on-site supervision by one of our site managers, who obviously makes sure that all of the planning that we do is actually undertaken. Any tests on the equipment, so the diverter has to be function tested. Everything like that, the site manager makes sure that it's followed as per the mine gas management plan. The next document, the basis of design. This is a bit of an oil and gas well document. Basically, it takes it sets out how we're going to design the well and what we aim to do and how we aim to do it safely. It's actually supplemented by other satellite documents, which I've mentioned previously. So the mine gas management plan, case and design, all of those documents feed into the basis of design document, which gives the detail behind some of the decisions and the designs. So the basis of design document might not have the fine details about the mine gas management plan. It might not have all the tables of risk assessment, but it has the outcomes in it. And it's meant to be like a central document with all of that information in. This document covers organisational design, technical and safety elements. So essentially everything collated into one place. It checks everything. So the safety, the case and design, the methodology of how we intend to reach the target. What is the target we're hitting? Where is it? What are the tests we're doing? Everything goes into this design document. It's about, I'm trying to think how many pages. I think it was about 400 pages long and something like 20,000 words in total. So it's quite a fairly hefty document. A detailed drilling program. So this comes out of the basis of design, and it essentially takes the program elements, everything we're doing and in what order. It becomes the go-to document for the project team and the independent well examiner, and they design their checklist off this document. It basically takes all of the information about what we're doing at what stage, what's going in the hole, what depths we're going to, and puts it in a chronologically ordered document that we can use to plan the works. For clarity, the document's actually split into what we call drilling sections. So it's generally done off a diameter. So ground level to 20 meters is drilled in whatever 762 mil. At that point, we stop and we'll put casing in. That would be a section, and it would get a section code. Within each section, you have to state what your objective is. So ground level, for instance, for that mine gas one, ground level to 20 meters, drill, install the conductor casing to prevent mine gas migration. It would set out the potential risks. Now, the potential risks, not for the overall project, but in particular that section of drilling. So when my site manager does his daily briefing in the morning, he knows what section he's in. He knows what potential mine workings we might be going through, so that might be a risk. Or we might just be drilling in a section where it's just sandstone and there isn't any risks. So it's specific to that section of the borehole. Obviously, it's different if there's welder and things like that. So that's why we do that. The bit type and sizes, so what diameter we're drilling, what bit do we intend to use, what bottom hole assembly on the stringer we're intending to use. The mud program, are we using lost circulation materials? What's the mud weight for that section? What verticality and testing programs, or what testing have we got to do in that section? Is it core, and have we got to do some packer permeability tests? It's all in there to that detail. Casing installation, what cement job have we got to do on the casing installation, and what weight's the cement, what mixture, and then the relevant process documents. So in that section, are we just drilling? Are we open holing? Are we coring? Are we welding? Are we installing casing? Are we doing a pump test? The processes would be are stipulated in there, and then our engineer knows what method statements and risk assessments the site staff have got to be briefed on before they start work on that day. Who will you want these documents? So these documents are given to the client, obviously, the client's health and safety management team, client's technical team. So the client's health and safety management team want to make sure we're doing the job safely. The technical team want to know that we're going to get all the data that they want in the right order. The coal authority, obviously, the governing body over entering their underground assets. So they want to see that we're doing it safely. The independent well examiner. In this case, that might not be on all jobs, but on some jobs you might have an independent well examiner who sits outside the job as an independent overseer of the works. They're not necessarily interested in what the data you're going to get. They're not bothered how much water there is or how hot it is. They just want to make sure you're doing it in the correct manner. It's safe. We've said that we're going to do it in this particular way, using this methodology, and every day they have a checklist, and they'll expect to see documents back to say that we're doing it safely. So every day they'll expect to see proof that all of the site staff have been briefed on the risks from that day. If we've installed some casing and cemented it, they'll expect to see a cement bond log, for instance, to prove that the cement's bonded. Or if we've installed casing, the checks and verifications on the joints. That sort of thing. And every Friday they give me a report and tell me whether I've got everything I need or I haven't. At the end, I get a certificate or I don't, to say that I've provided all the evidence that I need to say that the borehole has been undertaken as planned. If I need to change a methodology, as inevitably you have to, I have to go through a management of change with them, and they review it to check that what I plan to do is safe, essentially. The documents were given to the health and safety executive, and specifically the specialist on boreholes, who had quite a bit to say on them, to be honest, and did expect to see a lot of the well control that we had on this job. The local planning authority, that's more to do with the noise, dust and vibration monitoring, things like that. And obviously the site team get to see these documents, the detailed drilling programme especially. The next step is the design itself, which is done during the basis as design process essentially, but I'll go into detail of what we'll look at. Basically, we start from the base up. So the client will tell us what diameter the borehole has to be. That's obviously so they can get the right quantity of water out the hole, so they can fit the right size pump in the hole. As a drilling contractor, you generally start at the bottom up, put that finishing diameter, and you work your way to the surface. So this is a design for a job I've done, and you've got your geology down the left hand side. So we've worked our way from the bottom up, and every time we come across a problem, a potential problem where we might have to do a cement job, or we might have to put another conductor casing in, we can pick up on that. But if we want to finish in a set diameter, you start there, and then if we come across an issue where we'll have to put another set of casing in, you go a size up, come across another one, size up, and eventually you get to ground level and you finish in diameter, you start in diameter. However, that's based on the geology, the proposed geology from all the desk study work being correct. And like I said, you might not be lucky and have much borehole information nearby, and it might just be off the maps, and there might be unrecorded workings. There might be areas of gross flush loss, for instance, that you might have to case off. So you have to allow for a contingency. However, if you allow for a contingency, you're making your casing sizes bigger, your drilling sizes bigger, which all costs money. So how far do you go with that? How many contingencies do you allow for? Obviously, that's a commercial risk-based question, which is going to be project specific. But that's how we're based. It's basically you start from the bottom up and you look for your problems and increase sizes. Casing design, important. What is your pore pressure profile? So that graph, generally they're going to be normally pressurized. So you've got your pore pressure, and then based on your mud weights and your cement weights, you've got your pressures based on that on the same graph. Why do we need this? So we'll have to look at certain factors, so collapse strengths of the casing, which is why we need that pressure graph. The casing design needs to follow. You have to set out your minimum design factors, which might vary job to job, but generally the factors we'll look at are collapse and tensile strength. Burst pressure is not a massive issue. The re-injection well, you're very rarely going to have pressure in these boreholes like burst pressure. It's not like you're pumping oil down a pipeline. That you may need to force water into a re-injection well, but I can't see the pressures ever really being an issue. But for completeness, we'll look at them. And then what's your design life, which obviously affects the type of material you use. Assumptions we make that the casing will never be empty of water, the ground is saturated, there's no formation loads, and we'll apply a factor of safety of 2 generally. We then look at case load. So what are the worst case scenarios? This is checked against the strength of the casing proposed, and then checked against the collapse and maximum collapse and burst pressures. So our casing obviously has to pass. If we could say there's going to be X 500 psi of pressure on the outside of the casing, has to be able to withstand that with your factor of safety essentially. And we'll run through those. So the worst case tensile strength is when the casing's suspended from the crane on installation on the last length essentially. And the worst case for collapse pressure would be that the casing empties of water on the inside when you're installing it, but that's very, very unlikely to happen, which allows you to put in casing which it can have less collapse pressure than the pore pressure essentially. The materials, so cement for cementing in the casing, which has to be looked at chemically. Can it be resistant to the mine water? The same with the casing materials. If it's got a design life of 35 years, it's got to be able to withstand attack from the mine water. What specialist equipment? So I'm currently importing external casing packers from Belgium, which is a bit of an issue at the minute with the customs. Mud design for when we're drilling, and water on site. There's not many construction materials. As a construction project goes, you've got cement and your casing. There's obviously a lot of work around it, but there's not a great deal of materials. But it doesn't mean it isn't a problem, which I'll come up to. How do we construct a borehole? I'll quickly go through. I didn't know how much knowledge people would have of drilling, so I thought I'd quickly go through it chronologically. The first thing we do is we survey the location that we've been provided by the client's consultant over the hopefully over the top of the mine workings. We then install a chamber, and that's about 3 meters across, 2.5 meters deep. And you can see that the first conductor casing set into the base of that. That's where we start. That material obviously has to be disposed of, and that is the starting point for the well. Everything goes into this chamber after that. That's obviously health and safety wise. I was talking earlier, mine gas wise, that's now a bit of a potential confined space. So access to that after we started drilling is heavily monitored, and no one goes in there without a confined spaces permit and harnesses, for instance, to get them out, so no one goes in without a way of getting them out of that, without another person having to go in to get them, essentially. The next step, we drill to Rockhead to install the conductor casing to protect the local residents, and to direct our returns up the borehole. That's the starting diameter at Hebben. The smaller of the larger rock bit's 29.5 inches. The small one next to it for scale is an 8-inch rock roller. The next step is we install the conductor casing. All of the casing's welded, not threaded. That's a commercial decision. It's a lot more expensive to get your casing threaded. Obviously, you've got to go through a risk-based commercial decision on that, because you've got to weld over the borehole, which could have mine gas in, so you've got to put all the procedures in place to be able to do it. But the cost of actually threading the casing just far outweighs the on the commercial side for these sort of jobs, unfortunately. So it's welded in place and then lowered into the borehole before it's cemented in place. The wellhead is then attached to that casing, so you can see the diverter there that was shown in the previous diagrams is bolted onto a flange. At that point, any mine gas has to come up the inside of that. It can't come up on the outside, and it's all, like I say, pressure tested. Once we've done that, we'll drill the pilot well. In this instance, an example, it's not always the case. You might start drilling it like it's the final abstraction well, or the final reinjection well. But in this hypothetical project, we drill the pilot well to 200 meters, and we'll just open hole drill that. So the only returns we get are chip-ins, which we'll log as we go, which you can see in the sieve. Once we get to 200 meters above the target area, at this point we need more fine details, so start coring. We'll lower conductor casing to the base of the hole, and then lower the coring, J-bore-S coring string into the hole. We then core across all the targets and get all the information that we need to fine tune the design, because we don't know all the fine details. We don't know the exact depths. We don't know how much water there is, what the temperatures are, what the stratas are in between. We don't know until we drill the pilot well. So this is the design on the fly in a sense as we go. But we drilled in this instance from 200 to 296 meters, and we've got pretty much 100% recovery apart from the coal seams, which was good. We also then run other tests. So we did a CCTV survey as a potential, take water samples to confirm the water chemistry to make sure all the casing design, materials, spent's all correct. We can do a mini pump test to check how much water there is. Packer permeability testing. We also do verticality surveying as we go down to make sure the well is on the correct path. We do cement bond logs to check that the casing's correctly cemented in, and cement strength tests to check that it's cured correctly. We'll also obviously look at water temperature, and we'll also run other geophysics as we go down, so we can check the mud log and fine tune the depths of the strata in the areas that weren't cored. It's handy for picking up pool seams that were drilled through too quick, things like that we didn't pick up. We can pick that out in the geophysics and fine tune the borehole log. Once we've got to that point, we'll start the final reaming, and the reinjection well can start drilling once we know that it's a viable project. Once we've drilled it to depth, we'll install the final well casing and the stainless steel casing. We'll then go through a process of well cleaning. As you can see, they're not exactly clean. You have to get rid of all the fine material that could cause issues for your borehole pumps. So we go through an element of development and cleaning to get rid of all the stuff that could cause issues. And then we do a pump test to check the actual final flow rates. Challenges. What guidance is to be followed? So this is a new area. It's not new technology. We've been drilling boreholes and geothermal boreholes and water wells for over a century, I guess. So, but what guidance are we currently working to? There's nothing really for these mine water boreholes. They're not a standard geothermal project where you're just drilling into a rock strata. They're not really a site investigation borehole, although the pilot well is. We're aiming for mine workings which contain gas, so therefore do we take on this more oil and gas well approach where we say we're drilling into a hydrocarbon source. That then means, do we need an independent well examiner? Do or not? Different projects, there's no guidance out there that says you must have an independent well examiner. It's a client's choice if they do or not. Is there a need for all this detailed casing design, basis of design documents? Is that all needed? We provided it all to the health and safety executive, who then actually had questions and wanted clarifications on it. So is that, in a sense, saying yes, we do need it? Obviously, won't say yes or no. It's all down to ourselves to do what's reasonably practicable. The actual elements of doing those documents require an engineering input, not just a drilling input. So drilling contractors could do one of these jobs or win one of these jobs, and if it's not clear at the beginning before the tender process that they're going to have to write all these documents, they might not have the technical know-how or engineering in-house capability to do that. It took about 4 months for me to write those documents and to go through the review process to get them finally to get the certificate off the independent well examiner, and then and even at the end the HSE still had questions after that. So what is the correct methodology going to be in an industry standard? If these take off, like everyone hopes, and I hope they do, what is going to be the standard? Because they can have massive cost implications. Like for instance, the groundwater monitoring at the end of every day to make sure the well's static can add weeks onto a project. And these rigs are thousands and thousands of pounds a day to have on site. So adding a couple of weeks to a job, just measuring water levels at the end of shift, can add quite a lot of cost to a job. And if there's no set in stone guidance, we're currently in a position where some companies are going to price it not to do all of this, and other companies are. Who's right? And it's a funny one. It's a competitive advantage not to, but then you might, like I say, stumble into it and discover you're going to have to because you can't meet the IWE standards. Or it might just be that it's not good. You don't need diverters and you don't need this, and other techniques are fine. Just monitoring gas levels, like I do in site investigation every day in my other works. We just monitor the gas at the borehole, at the drill floor, and if there's a gas release, we stop work and we walk away until it's gone. What is the standard going to be? Groundwater levels and borehole diameter. This is a design issue. You don't have to drill your borehole to the final diameter and its full depth or the full length of the borehole. You could potentially, in this instance on the left, you would ideally want to put you hope the water level would rise into the larger diameter area of the borehole. What they've done potentially here is they've drilled down in a wider diameter, stopped, drilled through the base of the borehole and put drop pipe or open hole to connect it to the mine workings below. And they hope the water would rise to the expected groundwater level, but unfortunately it hasn't. That means the pump then has to sit inside the narrower part of the borehole, which means it's going to limit your flow. If you've planned to just drill it in a larger diameter all the way down, you can still fit your pump in down at that lower depth. It might have other implications, but at least you can get a pump in there that can pump the higher flow rates. Obviously, the design on the left might be cheaper. It needs less steel. It's smaller diameters. But if you set out to do that, you drill it, and you're just not doing a pilot well. You just set out to install it like that from the beginning. You've then got a bit of a problem because you'd have to start again and widen your borehole out, and your casing might be cemented in, your conductor casing. So you've got to do your plan on your worst case scenario. Without adequate pilot well there, it's quite risky to do the option on the left. Working in an urban environment, so like I say, these boreholes need to be near something that they're going to heat. So you can see that's my Hebburn site in the picture there. You can see what sort of environment it is, how small the site is, how close I am to people's windows, bedroom windows with these things. And the big drilling rigs, they're not quiet, unfortunately. And we do noise monitoring. Like I said, we've got a noise, dust and vibration monitoring plan on site, so we can't exceed certain levels, and it's monitored 24/7 and sends alerts to me and my site manager's phones if we exceed it. But it's still a nuisance. It's still going to be a noise in the background. It's still going to potentially annoy people and get people's backs up. You've obviously got all of the deliveries to site. Our site is actually split into a drill side and a compound side, so we're crossing a little road, which is actually an access road to the shops, which we can't block. It seems trivial, but it can add time to a job, just having an awkward setup. The site sizing as well can also have an effect on. We're quite lucky. The depth of boreholes we can fit our 2 rigs on that are capable of these depths, or Morgan's can't even. But if it was a bigger drilling rig drilling a deeper borehole, it might not be able to do both holes at once on that site. due to space, and then that's going to lengthen your program, which then increases your costs. And that's all because you're in a tight urban environment. You're not, unluckily, we're not going to be in fields a lot of the time doing these boreholes. Obviously, site security, children become an issue. We've had a few issues at Hebburn, not a lot, but we do attract a lot of attention. Increased traffic due to deliveries, and you get the old, are you fracking? You've got giant drilling rigs there, and people don't really understand the process. Obviously, a lot of that can be alleviated by good communication with the community before we get there, and we don't get it that often at Hebburn, but you are obviously attracting attention. Feasibility by pump test is a bit of an issue. So a lot of these larger schemes, if it's one building, it might only be 4 litres per second, which is a manageable amount. But say Hebburn, it's tens of litres, 40 or 60 litres per second. If you're pumping water out of a borehole to see how much there is, you've got to put it somewhere. Now that means you've got, well, where are you? You can't put it to mine water, so they're not going to let you put it in rivers or open bodies of water, and you might not have any anyways. You can't just put it into the drains because that's a lot of water. You might flood the drains. So where does the water go? Unfortunately, the only real place to put it is to drill a re-injection well. Now that means your client has to kind of take a risk and say that, and sink quite a bit of money into it to drill both wells to then test whether the whole thing's actually going to work. You can do some tests while you're doing the drilling, like you can do mini tests and run them for a day, but to check whether there's enough water to run for years, you need to run the test for about a month. At 60 litres per second, you're starting to get into millions of litres per day, and you've got to drill a borehole to do it, which means you've unfortunately got to sink a little bit of money, or a lot of money, and get to the point of even installing the borehole before you can even check that it's feasible long term. You can check there's water there, you can check it's hot enough, but the long term viability of it can't really be checked until the boreholes have been sunk, unfortunately. Water supply.
Hi,
Yeah.
Sorry, just to I don't know how many slides.
I've got about 3 or 4, and then I'm done.
All right, okay. No, just think about.
Yeah, I ran over. Sorry about that. Yeah, I'll quickly whiz through these ones. So, water supply in an urban environment, you need millions of litres to drill. I think we're up to about 3 million litres at Hebburn. A water supply from a hydrant isn't enough. They won't give you a 2-inch hose connection a lot of the time. So a lot of the time you need to store quite a lot of water on site, and unfortunately tanker it in, which unfortunately adds to the nuisance. Material procurement is an issue. A lot of the materials are from outside the UK now, which obviously tariffs and getting them into the country. Surge in construction has led to cement shortages, and companies have stopped making specific cement which is sulfate resistant, so I had to put a large order in for that, which is not good. Energy prices affecting steel and the cement as well can change the price of the raw materials from tender stage to actually doing the job. So there's a lot of who takes that risk on. The contractor's not wanting to take the risk that the price of steel suddenly shoots up. So that's a risk for the client, unfortunately. Target availability. So we're actually aiming for targets that are 4 meters across. At 300 meters, unfortunately, we can only be half a degree out and would miss the target. This is at Hebburn. That then you don't get multiple shots at it. There's only limited targets. You can see the corridors in the mine. So there's actually only a couple of places we can interact with it. And if you miss the target, you might screw up your one chance, essentially. Unfortunately, there's nothing you can really do to control verticality apart from set it up vertically and centralize your casing. But it can be knocked off vertical naturally, going through soft and hard rocks or pushing the drill bit too much, things like that. There are directional drilling processes out there for oil and gas well drilling, but they're very, very expensive and probably won't be commercially viable for these projects a lot of the time. So it requires just setting it up and drilling very softly and sometimes slowly. But there's nothing you can do apart from watch your verticality as you go and test it and make a decision whether it's strayed too much. Half a degree you wouldn't notice it. We were 0.4 out on the first borehole at Hebburn, and it ended up about 2.5 meters away. And at surface, you can't tell that them rods aren't vertical, unfortunately. And it could end up that you drill and miss the target, and then you've sunk £1 million into a borehole and you miss your target. And unfortunately, other workings open. So this is what we kind of think mines look like. In reality, they can be backfilled. So this is looking into one. It's been backfilled from floor to ceiling. Does that have an effect on the floor? Does the material affect the pump servicing down the line? Does it affect the re-injection rate? You can obviously see a lot of stuff coming out of solution there. So there's also those risks. You don't know what state the mine's going to be in until you drill the pilot hole. The abandonment plans might tell you it's there, but you don't know whether it's backfilled, open, and sometimes they're not correct anyways. And there's no guarantee. But enough of the negatives. Is this a good thing? Yes. Is there hot water? Yes. Can we drill to get it? Yes. But it needs a lot of careful planning and risk management. Is there currently enough guidance? No, but it's only a start, and it's a growing industry. And do people understand the risks and the potential for failure? I'm not quite sure at the minute. I think as people take on these jobs and they become more prevalent, people will start to understand that they're not just simple drill a borehole, that there are risks involved. And what is the answer? It's knowledge sharing, essentially, which we do at Hebburn. We've had everyone out on site visits trying to share these risks and the positives and the negatives and the lessons learned. So sorry, I had to rush through the last few bits there, but anyone got any questions?
Yeah, no, thanks for that. Very informative, and probably filled in a lot of questions we had about mine water heat sources, and particularly the actual physical process involved as well.
Yeah, there's a lot more to it than just drilling a borehole, unfortunately.
Yeah. Brian, there's been some questions asked on the chat. I don't know if you're just happy to just work through it, just answer them as best as you can, please.
Yeah. So who ultimately polices your procedures? It's currently, as I said, there's it's a bit up in the air about what not what procedures, but what guidance we're following, and a lot of it's client led. So some clients are going to say it's belt and braces and we're getting IWE, but you don't have to have an IWE if you don't want. But that might be the way. There are positives to having an IWE, and that they're verifying my works on behalf of the client, which is good. But essentially, it's the client's choice who polices it. And the client's technical team police the technical elements. I've got the IWE on mine, kind of policing the safety elements, but it's not really set out exactly what you need currently for these boreholes. Is there a risk of mine gas being released just when the well is being drilled, or is this an ongoing risk for the whole lifetime of the well? Mainly when we drill the borehole and we go into it would be the main risk. I suppose there is a slight risk when you're pumping water that you draw water from elsewhere, draw gas from elsewhere. But they're generally closed systems, so it shouldn't really be an issue, I wouldn't have thought. The water's just going up from one borehole through the plant and into the other one. It shouldn't be open to release it. But there is that risk, but I would think it would be quite low. If the mine's backfilled anyways, there's not loads of empty void for the gas to move in anyways. The gas is also more often in solution anyways. If you strike a body of methane, well, yes. So essentially, you're creating a positive head of water. So it's more about if the water level drops, then it could promote a release of water. In that sense, that's why we maintain the water head. So it's not a way of kind of suppressing it. It's more if the water level drops, we'll lose the pressure on top of it, and it could come out a solution or come out of the borehole in that sense. And that's why the diverter is there. So it always diverts it to the mud tanks and look and control it to the vent, essentially. How much time, money could it cost, and then realize this mine borehole hasn't worked? It depends on the project and how deep they are, unfortunately. I I wouldn't really like to disclose how much they cost, but they're not they're not cheap. The deeper ones are into millions, or over $1 million. It's a difficult one because the pilot hole itself costs quite a lot of money to do, and there's no way around doing these projects without that information. So you're always going to sink a bit of money into your pilot well anyways. But yeah, you could end up quite far down the line and find out that they don't work, because you need to undertake that long-term pump test to work out the long-term viability. You can do a test for a day, but you might be just pumping water out of a very discrete location beneath you. And 2 days down the line, that might dry up if there's no connectivity to the wider mine. So you can only do that once you've got the re-injection well, and you can do a full pump test, unfortunately. When are you coring? How do you maintain well core without and do you run a while when pulling the core? How do you ensure you do not swab when pulling in a back? The diverter, the slip in the top of the seal in the top of the diverter is big enough to pass our coring system through. When we actually unscrew the head though, the gas can come up the column. There's no way of avoiding that. It's a risk level. You can control it in the fact that you've got gas monitors at the drill location, and the driller is not stood directly over the drilling head when we undo the drilling head, but it's not deemed risky enough that would need a downhole BOP. Essentially, these boreholes, shallower ones, are drilled for site investigation day in, day out, and essentially if we do hit gas, we just monitor it. If an alarm goes off, we just switch everything off and walk away until it equalizes. It's not like the one problem with taking on oil and gas well methodologies is they think of drilling into a hydrocarbon that it's like a continuous flow. So you drill in, you hit gas, and it's just going to keep coming out of the hole until you can plug it. Mine gas isn't like that. You hit it, it's a pocket generally. It'll come out, it'll release, and it'll equalize. It's not like we're going to have to stop a continuous flow of gas. It's not like that. So that's kind of why we don't have blowout preventers, to be honest. What regulations say you need? There isn't really, but it's the lack of kind of structure at the minute about what needs to be on these jobs that then have pulled people towards getting independent well examiners from a verification point of view. But I say to clients, discretion, you don't need them. It's not an oil and gas well, technically. Lack of old mine is way more than likely. Answer to the accuracy of the mine plans, yes. Yeah, they are more than likely going to be out by the degrees I'm out in drilling. But you have to aim for something, and it's not just you have to aim at some target. We can't just say that it can be out and therefore it doesn't matter where we drill it. We've still got to aim in the best case scenario to hit it. And the other side of that is then that's my end of the bargain to the client. So I've drilled my borehole as straight as possible. I've hit where I said I was going to hit. If the mine plans are wrong, that's the mine plans were wrong. If Joe Bloggs in 1930 got his surveying wrong, then that's that. But I've done my end of the bargain, and that's all we can do. Unfortunately, if they're in the wrong place, they're in the wrong place. There are ways you can connect it, but potentially try and connect it. But yeah. That's unfortunately the case. Stephen, good evening. Oh, there you go. The Coal Authority requested that they were verified. So, Stephen, thanks for clarifying on that. So, in this instance, the IWE was actually requested by the Coal Authority before they'd issue that permit so that we could drill into their mine workings. That's the project manager from the Heaven job helping us out there. Thanks, Steve. Yeah, and the answer to the DCR regs apply. Again, it's No, technically no, but we've taken some on board in the sense that that we are drilling into hydrocarbon essentially. In the Hebben job, we've taken on essentially the ones we think are applicable. A lot of it doesn't apply. We're not on a platform in the middle of the North Sea, so we don't need to take on all of the regulations. We've just taken on what we think is applicable and what's relevant to these type of jobs, which is where like the basis design came from, and the detailed drilling program and things like that, and how we test the divert, function test the divert, things like that have all come out of it. But we don't take on every single oil and gas regulation because it would just turn it into a completely different project and probably make it unviable, to be honest, unfortunately. But that's what I was talking about going forward. We need to choose what is applicable to these jobs and what isn't. So it's clearer for people who are planning like ourselves, who are planning to drill these boreholes. It's like, what are we working to? And so all the jobs are working to the same standards, and that everybody who's tendering is also tendering to the same standard with the same. I'm not saying people are going to do it unsafely, but just so it's fair commercially, essentially. In that sense. Don't know if there's any more questions. Not that I know of, no. For the HE producing guidance, they reviewed the documents for this job. I think they are taking an interest in it, but there's no current specific guidance to drilling a minewater borehole over drilling a geothermal well or a site investigation well or a water well. There's nothing specific to it at the minute that I know of or planning to.
No, thanks, Brian, for running through them questions. Yeah, I think you've got through them all, and hopefully that's given everyone the knowledge that they need from this this seminar. So yeah, I think we'll wrap up there, Brian. We're just a little bit over time, but yeah, thanks for the presentation, and yeah, certainly improved my knowledge on minewater heat schemes. So
it's not a problem. It's hard to condense them into an hour, to be honest. They're quite complex jobs, so I try to give an overview of everything that's involved. But yeah, hopefully everyone enjoyed it.
Yeah, I think as well, Brian, you said that you were going to share the presentation with us, so and we'll host that on the CIBSE Northeast website. So if anyone wants to log on there and download it, they can do. So
definitely.
Yeah, no, excellent. Thank you very much again, and everyone enjoy your evening.
Thank you.
Thank you.
Thanks.
Cheers.
Thanks.
Bye.